Okay, kids, so we're in the next section of the textbook on projectile motion, and that's section 1.4. And we're looking now in grade 12, instead of just throwing something straight up, right? It stops. Remember that from grade 11, and then it falls right back down where we started. We're looking at throwing things off at an angle. So sometimes the angle is very close to straight up. And the path, as you can see here, looks like this. So the object that's moving is known as a projectile. All right. Sometimes the angle is a lot closer towards the ground. It's not quite vertical, but you still get this shape. And the shape, now I'm not the best artist in the world, you know that, is very much a parabola. Even if you kick something off a cliff, it's still a parabola, but it might just be one arm of the parabola. So this is the type of motion that we want to investigate, projectile motion. And the way we do it is we realize that if you take a look at this motion, it's best to analyze it in two dimensions with an x direction, x hat, and a y direction, y hat. It's best to analyze it like that. So we're going from a grade 11 situation where everything was one dimensional, up and down, right? That's all you had. It was all y. Moves up in the y direction, falls down in the y direction. Now, we didn't call it y in grade 11, but that's what it was. Now, if you take a look at an object, all of it can be described in two dimensions. For example, if we say this is the starting point, we can give it its initial x position and its initial y position. And then, I don't know, over here, it would have a final x and a final y. So position is no longer like here. It was just uh, position initial, position final, right? One dimension. That's not true anymore. All right, it's two-dimensional. Similarly, at any point in this object's motion, I can say, oh my goodness, there's a velocity associated with this object, but I have to say, look, there's a velocity here that's an x component. There's a velocity here that's a y component. And that could be true anywhere. Oh, what's the velocity here? Well, if I'm going to talk about velocity at any point along the path, there's an x component to the velocity and there's a y component to the velocity. Now, if you're going to talk about it without components, right, it would be sort of like this. You would add the x and y components. It would be like this. You would add the x and y components to get the velocity. But our way forward, if we're going to have success studying projectile motion, we need to work in components. We need to think of this as dealing with everything in x hat and dealing with everything in y hat separately. Similarly, we're going to have to talk about the acceleration of this object. Now, since we're on the planet Earth, you know what the acceleration is. It's g. And it's negative 9.8 meters per second squared y hat. When we ignore air resistance, that is the only acceleration. If you add air resistance, and we'll see that later on, you'll get other accelerations. But the simplest of these questions assumes that there is an air drag, right? That is, we don't have any of it. There's no air drag. That's the simplest way to study these. If you add air drag, it does become more complex. So let's continue with our look here. Section 1.4, projectile motion. Let's define it. It's the motion of an object, so it's launched. So if you take a look at an object, let's say that's the ground, this is the simplest way of doing it. It's launched. It's given some initial velocity, and that initial velocity, look what it says here, is at an angle with respect to horizontal or x at. So it's launched at an angle. That's a horrible theta. Let me fix that. It's launched at an angle to x, to the horizontal. And I'm going to remind you that the only way we're going to study this is through the component method. So we have to understand everything that's happening in x hat, horizontal, and everything that's happening in y hat, the vertical, and the only thing that binds them together is time. There's no how much time went off in the x coordinate, how much time went off in the y coordinate. No, time is consistent to both the x component and the y component. It's just a way for us to analyze it, to break down what's happening into x and y. But time goes by in both. Time is common to the entire motion. So here is a simulation. Here is a simulation of something that's shot up into the air from a cannon, and it's shot from 0 meters in the air, right? So right here would be our initial position. It would be 0 meters x hat, 0 meters y hat, and it's shot up into the air. So let's just do that quickly. Boom, there it goes. Now we're going to talk about it in greater detail, but there's your parabola. There's projectile motion. So what I've asked the simulation to do, and I've put a link to this simulation, is show the velocity vectors in components as this is shot up into the air. So I'm going to shoot that out. I'm going to pause it. So here is the x component of the velocity, and here's the y component of the velocity as this object is in midair. Now I'm going to just slowly push this onward. If you take a look here, the x component of the velocity never ever changes. It doesn't change during the whole parabola of the projectile motion. That's because there's no air resistance. There's nothing to slow it down. There's no force acting on it in the x direction. But if you take a look at the y component of the velocity, look, it's getting smaller and smaller as the object goes higher and higher into the air. That's good, because if that y component of the velocity wasn't getting smaller, it would be shot up into the air and leave the earth, but it doesn't. It slows down, just like you learned in grade 11, and at the vertex of the parabola, let me see if I can get that. The vertex of the parabola right there, look, there's no y component to the velocity. It's all x component. So this is very similar to what we learned in grade 11, that when you throw an object straight up, it stops, and then it comes back down. Well, the same thing here, except we've added this constant x component of velocity. Let's keep going. And look, slowly but surely, it starts to speed up as it's falling downward. Look at this y component of the velocity. It's getting bigger and bigger and bigger and bigger until finally, come on, there we go, it hit the ground. Okay? So really what we're looking at here, if you think about this, is that we've got a y motion, y component motion that's very similar to an object that's thrown upward and then falls back downward, combined with a x component motion, an x component velocity that is actually non-uniform motion. The x component of the velocity is constant. It doesn't change. There's no x component to the acceleration. So let's erase that path. And let's show the acceleration vector as we launch this. Here we go. Oh, what's going on? There we go. Take a look at the acceleration vector. It never changed. Let's do it again. Look at the acceleration vector. It's your old friend, negative 9.8 meters per second squared, and now we add y hat to it. That's all that's acting on this object is gravity. That's it. The acceleration is just my friend and yours, G. What's up, G? Okay? There's no air resistance in this situation. And finally, just to show you what force is acting on this object, the force that's acting on the object is only one force. There it is. It's constant during the entire path. It's the force of gravity, Fg, also known as weight, and it's pointing straight down always. There you have it. Now, can we get more complex with this? Yeah, sure we can. We can add air resistance. It's quite a complex solution, but I'm going to show you this object being launched with this air resistance. Oh, Nelly, come on. There we go. Air resistance now. Okay. Now I'm going to take off the air resistance, launch it again. Come on. There we go. See, the path is different. It's not that perfectly symmetrical parabola. So look, this is the first time you're studying projectile motion. Let's stick with no air resistance. And later on, you could look at adding air resistance. It's not as easy as you think. Okay? Not as easy as you think. So that's where we're starting here in grade 12. And I've put a link to this simulation so that you can tool around with it. It's fun. If you really want to investigate drag more, you can change the diameter, the mass, the drag coefficient, which is a non-unit coefficient that tries to describe how the surface interacts with the air. It's more complex than you think. And if you want to tool around with that, if you have time, I know you're quite busy, you can do that within here. But we'll leave it at that for now. So here's a diagram, and I know it looks kind of jumbled, but I'm going to take you through it step by step. So let's say there's an object that's shot upward from the ground, at 25 meters per second at 20 degrees to the horizontal. So what you would draw is a red line here. You would draw the red line. Let me change that for you. There you go. You would draw the red line. There it is. Draw the red line to represent this initial velocity of 25 meters per second. And then you would draw the red theta in here, saying, look, this is being shot up at uh, 25 meters per second. Now, the other thing you got to remember is that velocity can be broken down into velocity initial x component and velocity initial y component, because this entire situation is happening under an x hat, y hat Cartesian plane. So I've kind of drawn it in yellow here. In the back of your mind, you always have to think this motion is happening on this x hat, y hat Cartesian plane. And then the object, what it does is it starts out here, and then I've drawn this parabolic path that's pretty close to a parabola in pink. So that a little bit later in time, the object will be right there, okay? And when it's right there, it has a velocity x component, and when it's right there, it has a velocity y component. And these are just the components of its velocity at that point. Every time we think about velocity, we break it down into x and y. Every single time. And we learned from our previous discussion that this x velocity never changes. Then a little bit later in time, it gets to the vertex of the parabola. And we saw it in the animation. At this point, the y component of the velocity is 0. The x component is still there. It is unchanged. It is constant. And then it moves a little bit further, and let's say the object is right here now. All right. What could we describe about the object right there? Well, we could say a certain amount of time has gone by. How much time has gone by from when it started to get to that point? So that could be information, right? What else can we say? Well, it's got a new position here. It's at a new position. Okay, it's got a new position, but when you think of position now, you got to think, what's the x component of that position? What's the y component of that position? What else can we discuss about this here? Well, it's got a certain velocity here. Vx and Vy are the components of that velocity. Yes, we could draw the full-blown vector in green, but it wouldn't be helpful to our studying of this motion. We would need to consider that x component of the velocity, which doesn't change. We would need to consider the y component of the velocity of that object at that position. So everything except time, which is a scalar, has to be broken down into x component and y component. Even the acceleration. What's the acceleration during this entire path? Well, if there's air resistance, it can get quite complex. If there is no air resistance, then we can assume that all of the acceleration is in the y direction, and it's our old friend negative 9.8 meters per second squared y hat. And we're going to spend our time with no uh, air resistance. It's just easier. So what does this all mean? It means you've got an object that's launched at 25 meters per second, 20 degrees to the horizontal, which means it has an x component to its initial velocity, a y component to its initial velocity. We can assume there's no air resistance. So the only force acting on it is force of gravity. Remember that from grade 11? Mass times the gravitational field strength near the surface of the Earth, also known as weight. That is the only force acting on it. And that is why, since it's the only force acting on it, that G is equal to acceleration in the y direction, negative 9.8 meters per second squared y hat, and that acceleration in the x direction is 0, which means there is never a change in the x velocity, x component of the velocity. That x component of the velocity is always constant. These are critical ideas we have to understand. So what's the next thing we got to talk about here? Well, the next thing we have to talk about here is just like we had a certain set of equations when we were studying motion, non-uniform motion in grade 11, there's a certain set of equations that we have to know when we are studying projectile motion. And since we're going to study projectile motion in components, these equations that are going to be part of our toolbox are divided into x hat equations and y hat equations. So let's start with the x hat equations. It's the simplest set of equations because in x hat, all the motion is uniform motion. So first off, x hat, x component of the acceleration, 0. Change in the x component of position is x final minus x initial. Velocity x component is equal to displacement in the x component divided by time. That's it. There's no acceleration. Then we move over to the y component. Well, we know that the acceleration in the y direction, that's a better y, acceleration in the y direction is our old friend g. What's up g? And it's negative 9.8 meters per second squared y hat. We now can look at a change in the y position, the y component of the position. Delta y is equal to y final minus y initial. So really, if you take a look here, our old friend, change in position, which was d final minus d initial, that's too simple. We can't use that. We had to break it down into components. And since all of the accelerations are dealing with y acceleration, the equations that were familiar to you, acceleration is equal to final velocity minus initial velocity all over time. It's final velocity y component minus initial velocity y component, all divided by time. The only thing that's in common to both sides of the ledger here, the x side and the y side, is time. Time is a scalar. There is no such thing as time x component, time y component. It's the same for both. As time goes by in one, it goes by in the other. Similarly, you might have remembered this equation here, delta D equals. We can't use delta D. You have to break it down into components. change in the y component of the position is equal to half initial velocity y component plus final velocity y component. So all those equations with delta D, they're gone. Have to be broken down into x and y. Similarly, delta y, so change in position y component is equal to final velocity y component squared minus initial velocity y component squared all over 2 times the acceleration y component. And the last two, they're like the twin equations here. Change in position, y component of that change in position is equal to initial velocity, y component multiplied by time, plus half of the acceleration, y component, delta t squared. And the other similar one, change in position y component is equal to final velocity, y component, minus half acceleration y component delta t squared. Remember these equations from grade 11 really had a plus sign here, and that was initial. This had a minus sign here, and this was final. So these are your new sets of equation for projectile motion. You need to know these. Some of them are quite similar. You had the one side here in X that was all the uniform motion components. But on this side here, it's a rewriting within the Y component of our familiar non-uniform motion. It's an awful M. Looks like a mountain range. Anyway, non-uniform motion uh, equations now broken down into components of Y here. So we're going to continue here in a very special situation, a very specific example of projectile motion. What specific example of a projectile motion? Well, it's when the object leaves its position, probably the ground, and it goes through the air and falls back to the ground. Or mathematically speaking, y initial and y final, they're equal to each other. They're both at 0 meters when you're looking at the y-hat. Vertical. When you have this situation, there's a certain symmetry to this. And the object is launched with this initial velocity, which can be broken down into its components. But when it hits the ground, the magnitude of that initial velocity will equal the magnitude of this final velocity. There's a symmetry here. And the angle here that's above the ground, which we're calling theta, will be the angle below the ground if we want to give a direction to that final velocity. There's a symmetry here. There's a symmetry. Similarly, the time it takes to go up to the vertex of the parabola and the time it takes to go down from the vertex of the parabola to the ground, they're equal. The total time is adding them both together, as I've written right here, but these two values are equal. We saw that in grade 11 when an object was thrown straight upward and came downward. There's a symmetry here. What else is symmetrical or known? The x component of the velocity never changes. And if you take a look at this final spot right here, okay, right here at the end, if you were to take a look at the y component of the initial velocity and the y component of the final velocity, they would be equal in magnitude, but opposite in direction. So this y component of the final velocity and this y component of the initial velocity, they're the same magnitude, just one's pointing up and one's pointing down. I've said this a million times during this screenshot. There's a symmetry to this. When you have this special, when you have this special situation, of the object being launched from the ground and then it's allowed to fall to the ground. The y final and the y initial are equal. They're both 0 meters. They have no height. Are all projectile motions like this? No, they're not. But this is the simplest one. So, are we ready for an example? I hope so. We're going to do a full solution example next. Okay, so here is our first example. This is your first full-blown projectile motion question. Example, a ball is launched with an initial velocity, right, that has a magnitude of 113 meters per second at an angle of 60 degrees above the horizontal from the top of a cliff that is 40 meters high. And to solve this and all other projectile motion questions, I expect you to use graphs. Very important to organize yourself, very important to draw a diagram. So let's do that right now. So what I do is I draw the diagram, I make an X and a Y. So here's your X and Y right here. And from here, the object is shot up with an initial velocity that was given to us 113 meters per second. And I consider this spot right here to be the initial position of the object, X initial, Y initial, and I'm going to give it a name. It's always useful to give it a name, and always useful if we know it, that we're going to say, look, since we're starting from here, it's kind of a convenient way to do this. Since we're starting from here, I'm going to define this spot right here to be 0, 0. And then the object is shot up from there, and it's shot up from there, and it's going to have a velocity initial X component. I draw it right there. And a velocity initial Y component. I draw that. I draw the full-blown velocity vector. I put theta in because I know it's shot at an angle. And then the path will be a parabola. So I draw the parabola. There it is. Now this is shot from a cliff, so it's going to land below it. So there it is. It lands right there. And this will be its final position, X component final of position, Y component final position. But since I know that the object was shot from 49 meters above the ground, the cliff was 49 meters high, I know that right here, if this was 0 meters, this is below 0 meters by negative 49 meters. So I actually know what my Y component of the final position is. It's negative 49 meters Y hat. I can put that in there. I can put that in there. So because of that, I can write out this equation right here. Delta Y is equal to Y final minus Y initial. It's negative 49 meters Y hat. That's the final Y position. It started at 0 meters, so its delta Y, its change in position Y component, is negative 49 meters Y hat. So if you can do that in the given, I highly recommend you doing that. Next part. Look, I told the class in the previous part of this lesson, let's go back to the top here. We've been given the velocity as an angle and a magnitude. We can't solve these problems unless we break everything down into components. So that's what we're going to do. That's what we're going to do. So here is my velocity initial. I need to find out what velocity initial X hat is, and I need to find out what velocity initial Y hat is, knowing the angle and the magnitude of the entire vector. Now, you may be saying, sir, isn't this a calculation? Why are you doing it in G for given? Well, it is a calculation, just like the delta Y is a calculation, but I consider them to be preliminary calculations. It's really just trying to flesh out what all your given information is. It's not trying to calculate an explicitly defined unknown or required quantity. So we know the magnitude of this is 113 meters per second. We know that theta is 60 degrees, and we break this initial velocity vector into its component. And you know how to do that from before. So velocity initial X component, 56.5 meters per second X hat. Velocity initial Y component, 97 4.9 meters per second y hat, and they're both positive components here. I have taught you the component method in the past. I don't have time to reteach it here. If you have to go back and watch another lesson, the previous lesson on this, go ahead and do that. And you'll notice that what I said in that lesson is that the component method, breaking vectors into two components, the x part and the y part, which together represent the entire vector, is part of this entire course. That I cannot stress to you how important it is to understand the component method and to break vectors down into their x hat components and y hat components. So that is our look at the velocity vector, the initial velocity vector. What else can we remind ourselves of here? Well, we remind ourselves that the acceleration is completely in the y direction because there's no air resistance, right? And we might also want to remind ourselves that right at the very vertex, the velocity is all x here. The velocity y component at the very tip of this parabola is 0. We talked about that previously. So so here we're using graphs, remember, so GR, R for required. What do they want us to calculate? Well, one of the things I'm going to ask you to calculate is the total time. That's from when it is launched from the top of the cliff till when it gets to and impacts the ground. So we're going to call that time delta T total. That's required A. Required B, what is the final position of this object in terms of X component? That has a very special name. It's usually called the range of the projectile motion. And then when it finally impacts the ground, what is the final velocity of it? Specifically, final velocity y. How hard does it hit the ground, if you will? Next, required D, how much time did it take to get to the very top of the motion, which we call y component of displacement, the maximum, the height of it, high as it ever gets. That's part D. So let's take these each in turn. So just like you did in grade 11, you need to go and back and look at your equations. You need to go back and look at your equation and select the appropriate equation that will let you solve the problem. Now, sometimes the equation is on the x component side. Sometimes the equation is on the y component side. It depends on the question. Some questions it's best to start in x component, some best to start in y component. How do you know? Well, it comes with experience and practice, like anything else. Solving projectile motion questions take a lot of practice, and I'll give you opportunity to practice that. So, here we go. We want to solve for the total time, which we're going to call delta t. So I have decided to pick this equation here because delta t is in it. That's what I want to solve for. Acceleration in the y direction is known. Final velocity, excuse me, initial velocity in the y direction is known. I beg your pardon. And change in position y component is known. So look, known, known, known. The only unknown is the time. So that's my analysis. I picked this equation for those reasons. And then S for substitute, I'm going to plug in numbers. So what was my change in position y component? Well, it was on a cliff and then it fell below the cliff. It fell by negative 49 meters y hat. Here was its initial velocity y component. Delta t is what we're going to solve for. Okay. And then half of the acceleration y component. Well, we know acceleration y component is negative 9.8 meters per second squared. Well, half of negative 9.8 is negative 4.9. So that's why that is in there. Ooh, forgot a y hat. All right. So I just plugged in numbers there. Next, oops-a-daisy. I rearrange this equation by bringing this value to the other side. So it leaves me with nothing on the left-hand side, 0. So this negative 49.0 meters y hat comes over to the other side, but since it comes over to the other side, I have to put a negative sign in front of it. Everything else stays the same. Well, I hope you've recognized that this is really a quadratic equation in which we can use the quadratic formula to solve for delta t. Here is the a term of the quadratic formula that we're going to use, negative 4.9. Here is the b term, positive 97.9. Here is the c term. It's positive, negative, and a negative give us a positive. So here's your c term. So you can plug that into the quadratic formula. Delta t is negative b plus or minus the square root of b squared minus 4ac all over 2 times the a term. I know you all know the quadratic formula. So you can solve this. I think some smartphones you can download a quadratic formula app, right? Or some calculators even have that built in, whatever you want to do. I'm not here to test if you know how to use the quadratic formula. That was done in a previous math class. All right. And it gives us two roots. It gives us two roots. And one of the roots is 20.5 seconds, and the other root is negative 0.48 seconds. You can't have a negative time. So this is known as an extraneous root. Makes no sense. So using our intelligence, we select this as the how much time does it take to hit the ground. So we've done it. We've calculated our first required. Next, how far does it get in the x direction over this entire motion? Well, we want to find position final x component. There it is. Well, we have delta x is equal to delta x final minus x initial. We rearrange this equation and we get x final is equal to delta x plus x initial. But x initial was 0. Remember, we decided that the start point would be 0, 0. So that means x final is equal to delta x right here. Well, is there an equation on the x side of projectile motion that lets us study it? Yes, there is, and it's only one equation. There it is. Velocity x direction is equal to delta x over delta t. It's the old v is equal to d over t, but it's a component now. So we rearrange it, and we get delta x is equal to velocity x component all multiplied by time. So we plug that in. X velocity never changes. So that's pretty easy to find. I calculated that velocity initial x component. How much time is it in the air? 20.5 seconds. I multiply, and I know that it's moved forward by 1.16 times 10 to the 3 meters x hat. That is your x final. So I've calculated that. Next, the next thing they wanted us to calculate was velocity final y component. So in your analysis, where you're picking the right equation, this is a good equation to use. Why? Because it's got VF y in it. That's what I want to calculate. And I better have all the other bits of information. Do I know the velocity initial y component? Yes. I calculated that by breaking down that initial vector. Do I know acceleration in the y direction? Sure do. It's g. It's my old friend. What's up, g? Do I know how much time it's in the air? Yep. Just calculated that. So I'm going to rearrange this equation. We did it many times in grade 11, and here it is. Then I'm going to substitute in the values. Look, I use my nice brackets. I always use brackets. I put the unit. I put in y hat. Look, see? And I get final velocity y component is equal to negative. Ooh, that's a good sign. I got a negative answer because it's going to hit the ground. Negative. It's going downward. Negative 103 meters per second y hat. Remember, the final velocity x hat is equal to initial velocity x hat. Velocity x direction is constant. There's no air resistance. So you don't really need to recalculate that. We know it never changes. So we've calculated that. Terrific. Next, they want us to calculate, remember this here situation, how much time does it take to get to the top of the parabola, right? Remember there was the cliff and it landed below the cliff, but how much time did it take just to do that up bit? So time up, right? We're calculating time up here. Time up, time up. Well, I need to find an equation that's got time in it because I'm going to be calculating for that. So I've picked this equation right here. Look, luckily it's got time up in it. Terrific, terrific. Well, do I know the acceleration of this object as it makes its way to the top of the motion? Yeah, it's my old friend, your old friend, what's up, G? Do I know the initial velocity, y component, with which it was launched? Do I know that y component? Yeah, I do. I calculated that. Check. Do I know the y component of the velocity when it's at the very vertex at the very top? Yeah, that would be my final velocity y component. And I know from the discussions, from our lessons, that that's 0. For that instant at the very top, it's 0. So I take this equation right here and I rearrange it to give me this equation. I rearrange it. Plug in the values, final velocity y component 0, initial velocity y component positive 97.9 meters per second. Acceleration in the y direction, my old friend and yours, what's up, G? I do the calculation, it took 10 seconds to get up. That's your very first projectile motion question. Are they long? Yeah, they are. Does it take a lot of time? Yeah. Do you have to organize your solutions and structure them and draw a proper equation and be patient with yourself because you're going to get better at these until, with practice? Yeah, all of those things. And we're in grade 12 physics, university physics. That's the way it is. All right? But remember, I'm on your side. And I'm going to give you a ton of these problems to do, and you're going to practice them with goodwill. And when you don't understand, you're going to ask me so I can help you. And we'll get through this. Other people got through it, and you'll get through it too.